Okay, why don't we continue now? And we will have second part of our lecture material here. This is a shorter lecture kind of introducing exercises 6 and 7. So yes, I guess hopefully you can see that. And yeah, this is basically a set of exercises that are sort of nominally titled Quantitative Thermochronology. So this is essentially where we're going to bring together some of these ideas we've dealt with in the earlier exercises like Dodson's method and heat transfer to try to interpret these thermochronometer ages. And we're going to do that using data from a nice looking area like this. So this is a picture just found on Wikimedia Commons of the Himalaya in Bhutan. It's a lovely landscape as you can see clearly. And this is an area where I have worked earlier with some colleagues, and we've collected, they have collected rock samples and dated them using different thermochronometers, and then I was involved in the modeling part of this data. So we have here a kind of map of Bhutan, and you can see where we are here in the inset map. So eastern part of the Himalayas over here, and we're in this western transect in the eastern part of the Himalayas. So the western transect in Bhutan, there's an eastern transect of data as well that we won't use, that's described in this article from 2014. But there's a bunch of different dating methods that were used for samples that were collected here. So all the colored dots that you see here are rock samples that were collected and dated using different minerals like apatite, uranium, thorium, helium would be in green. That's one of use or of interest to us perhaps. Zircon, uranium, thorium, helium in pink, also of interest to us in this, this final two exercises. And these rock samples were collected basically going in a north-south transect across the western part of Bhutan, and all the way from the foreland, where there's essentially no mountains, across these different major faults up toward the margin of the Tibetan Plateau. So covering, in this case, as you can, is there not a scale on this here? I guess there's not. But this is about maybe 150 kilometers, or maybe even a bit more than that in terms of the length of this transect over which these rock samples were collected. And if you look at the age data that was produced here now it's kind of shown as like a, this is like a swath profile of the topography. So just jump back here for a second, and we kind of take a cross-section line or sort of a slice through the middle of this western transect and just project everything onto this cross-section. You get a plot that looks like this. So here in the heavier black line would be like the average elevation across this western transect. The highest elevations would be the top of this gray shaded region, and the minimum elevations as a function of the latitude. So going from south to north, from left to right. Those lowest elevations would be the minimum at that latitude. And then you have all the age data here that were produced, and you can see there's quite a bit. So just for the uranium, thorium, helium ages, for example, you can see there's a lot of these green and pink points, and we can use Dodson's equation to predict those ages. So actually the green and pink ages are what we're going to be using in our exercise for the last 2 weeks in the course. So we have this pattern of these age data, but as you can imagine, it's not like they're all showing the same age. So it can be a little bit challenging to interpret what this actually tells us about this landscape. And so that's part of the reason why we're going to bring in a numerical model to try to help in interpreting this age data, because the variation in ages that you see here might make it rather difficult to figure out things like the average rate of erosion of this landscape over the kind of timescales of a few million years. So what we're going to do is we're going to use our skills and a few new things we'll add into our little toolkit of functions to create a way to estimate the exhumation rate of rocks over millions of years using thermochronology and a little bit of Python. And so this exhumation that we have, remember this is a process that brings rock from depth up to the surface, could result from erosion or could result from tectonics. In our case here, we're in a convergent setting, so all the exhumation would be driven by rocks being eroded at the surface. So this gives us a long-term rate of erosion of the rocks that we can then use to come up with this long-term exhumation rate estimate based on the ages that we have in our data set that are shown, for example, here on the previous figure. And actually, sorry, I guess when I described this elevation swath, I described this incorrectly. It says plus or minus 1 standard deviation in the elevation. So it's not a swath profile in the sense that this is the minimum elevation. That's minimum for the -1 standard deviation. The maximum is +1 standard deviation. So sorry about that. So yeah, we're going to estimate exhumation rates. And one way we could do that, if we wanted to do the kind of quick and dirty method, would be to take something like a thermochronometer age and assume some constant geothermal gradient. So we could say like 20 degrees C per kilometer is how much temperature increases from the surface down into the crust. And we could use this age and this gradient in temperature to come up with a long-term rate of exhumation. Well, how does that work? Well, if we have an age here, for instance, 12.3 million years for some dated apatite crystal, if we assume a closure temperature of 75 degrees C and a typical geothermal gradient of 20 degrees C per kilometer, what this age would give us then is the time it took to go from 75 degrees C up to the surface, which we could assume is 0 degrees just for the sake of simplicity. How would you find an exhumation rate from that? Well, all you do is simply find the depth to the closure temperature and divide that depth by the age, because you know it took that many million years to travel from that depth up to the surface. So if we plug some numbers in here, and we do things kind of, again, simply, assuming its surface temperature is 0, we would say that our closure temperature, 75 degrees C, divided by the temperature gradient, 20 degrees C per kilometer, would tell us the depth to that temperature would be 3.75 kilometers. That's probably relatively easy to see from this temperature gradient that, yes, you would have to go down to 3.75 kilometers to get to 75 degrees C. Now, if we know that it took 12.3 million years to go from that depth to the surface, to travel a distance of 3.75 kilometers, then we can come up with an average rate of exhumation, in this case, of 0.3 kilometers per million years, 300 meters per million years, or 0.3 millimeters per year. Those are the same units. So kilometers per million years and millimeters per year are going to have the same number. So that's one way in which we can do that. The problem is that if we assume the temperature gradient is constant, that's not necessarily a very good idea, because there's a lot of things that actually change the temperature gradient with depth. So a better approach would be to use a 1D thermal model, which it just so happens we have available to us from exercise number 4. So back in exercise number 4, I think you may have actually made a plot somewhat like this. Here, this is a steady state geotherm. So remember, this is the temperature you would calculate for constant rate of exhumation that's not changing over time. And as you can see here, this is a curved line. It's not a straight line. So in other words, this geotherm is changing with depth, though it's not a straight line, and therefore not necessarily a good approach to assume a constant gradient in calculating a thermochronometer age, for example. But the bending of this line, the curvature here, is basically a function of this rate of exhumation that's given here, or this advection velocity as we referred to it in exercise number 4. So the bigger this Vz, this advection velocity term, gets, the more curved this line is going to be, because this particular solution assumes a temperature of 0 at the surface and 1300 degrees at 130 kilometers depth in the plot. Those 2 points are pinned, and so essentially as you change this velocity, if it goes to a higher advection velocity, you'll get something that's more of like a kind of flat curve near the surface and then curves over more sharply. And of course, if it was a lower velocity, you get something that's more like a straight line. So the amount of bending is going to be a function of this rate of advection. And that's perhaps the important thing to consider in our example here. So what we have is a 1D model that can allow us to calculate a temperature and calculate the temperature at different depths. Now, if we want to simulate a sort of cooling of some rock sample, we need to then include and somehow calculate a cooling history for that rock sample. So we know it's going to end up at the surface at time 0 MA, so today, with a temperature of something like, we could just say 0 Celsius for the sake of simplicity. And we know that the temperature history is going to be somehow related to this advection velocity, because that's going to affect, for instance, how much this line is curved and how quickly the rock travels up toward the surface. So if you think about the advection velocity as the velocity at which the rock is moving up toward the surface, then of course, the faster it's moving toward the surface, it's also going to be traveling through different parts of this curve at different times. So we can use this advection velocity to come up with a cooling history. How does that work? Well, we can basically figure out that, okay, if we know it's at the surface today, then based on this velocity, we can figure out how deep it was at different times in the past. And that reason for that is that every sort of time increment we might consider in this rock's cooling history, it would have traveled by some time multiplied by the velocity. That would give us some distance it's moved closer to the Earth's surface. So putting this in the context of like a picture like what we were just looking at for the geotherm before, you would have some rock sample that maybe started out here at some depth around 70 kilometers at a temperature around 1,000 degrees at time 1. At some later time, it's traveled to a shallower depth and a sort of cooler temperature, and it's sort of continued that progression as you move up toward the surface. With time, because this velocity we're going to assume in our example is constant, the distance between these points in terms of depth would be constant. So the sort of steps between each one in depth would be constant, but the temperature difference between them will change as a function of this kind of temperature curve that we've calculated. So you can see, for instance, the temperature difference between the final 2 points, it's something like 300 degrees between 300 and 0. Whereas in the first point, it was maybe about 150 or maybe not even 150 degree difference. So where you are in the curve will make a difference. But essentially, all we need to do to calculate the temperature history is to know what depth it was at some different time in the past. So T1 here would be a function of being at this depth at this time T. Again, we have all the tools now, I think, with the exception of producing some kind of depth history, to create this temperature history. And once we have a temperature history, we can use that to calculate a thermochronometer age, because essentially what we would know is, let's say we've calculated our closure temperature, we would know the age would be basically the time at which the temperature and this cooling history goes below that closure temperature. And that would be then our cooling age, or our thermochronometer age. So the basic concept, just to kind of go over it in general, and this is what you'll work on in exercise 6, is we're going to create a depth time history. That'll be a function of whatever advection velocity we're going to use and however long we want to simulate the kind of cooling of the rocks. But we'll create this depth time history. We'll then generate a thermal history using that depth time history, because just like we saw here, if we know what depth we're at whatever time, we can calculate what the temperature was at that depth and at that time to create a temperature history. So we'll produce this temperature history using our depth time that we can create. That'll be the first thing that we do in our kind of set of steps to getting let's put that back up. So if we're going to work in the direction of getting a thermochronometer age, the next step after we have the depth time history is to create the temperature history for whatever the velocity is that we're using, Vz. We can use that thermal history to calculate a closure temperature, because you remember the closure temperature depends on things like the rate of cooling. So the kind of cooling history will be important to figure out what the closure temperature would be. And we can use the Dodson function from back in exercise number 3 to calculate that closure temperature. And we can basically go through a process where, as long as we're above the closure temperature, and we'll know that from having calculated it before, we will continue to calculate a new closure temperature. As soon as we go below the closure temperature in this thermal history, then we can say, okay, we're no longer going to have to update what this estimated closure temperature would be, but that'll make sense, I think, when you start doing it. Once you know the closure temperature, you can use that to find the point at which in your temperature history you cooled below that closure temperature, and that will give you your predicted age. So if the closure temperature was 75 degrees C, for example, you would look at the thermal history you have and say, okay, at what time did the temperature in this thermal history go below 75 degrees C? That's going to be your predicted age. And once you have a predicted age, we might have, for example, here some measured ages, like with a measured mean age and some standard deviation, and then we would have a prediction like this white square here, and we can use our chi-squared function that we had again back from exercise number 2, I think, to calculate the goodness of fit, to see how close is this predicted age to the measured age. And then we're going to repeat these steps 1 through 5 until we reach a good fit. So we can, for instance, change the advection velocity and make it faster or slower and see, does that make the fit to the measured age better or worse? And the point is that you kind of iterate on this process until you reach the point that you feel like you have a good fit to your age data. So that's the kind of big picture for what's going to be going on in exercises 6 and 7. I might ask at this point, do you have any questions, or does this make sense, the kind of approach? It's a bit abstract maybe at the moment, just because it might take kind of sitting down in front of the computer and looking at things for all the pieces to kind of fit together nicely. But we have a lot of the components we need to predict these thermochronometer ages already from earlier exercises, and now we're going to put them together to do that. So yeah, does this make sense? I don't know if you want to say something in chat or give a, I don't know, thumbs up or something like that. Or if you have questions, of course, you can certainly ask for some clarification. I've got at least 1 thumbs up, so that's good to see.
I just have a question. So like, let's say that you have to repeat steps from 1 to 5 until you get a good fit. But like, don't you have to like change something? Wouldn't you, like, I'm just like kind of confused, because like if you just repeat the same thing, you have to change something for it to be like a good fit, right? So like, what do you need to change?
Yeah, good question. So I mean, in this example, the thing that we would be changing would be to change the advection velocity. So to make the advection velocity faster or make it slower, and then see how that affects your age. Because of course, if that will change the predicted age, and then that will also change how well that predicted age fits the set of measured ages that we have. So, if you start out with a slow advection velocity and a big goodness of fit, like your chi-squared value is very large, then what you would see is that if you increased the advection velocity, so like let's say you started out with 0.5 millimeters per year as the advection velocity, and what you saw is you got a really big goodness of fit number. Your chi-squared number was really big, and you increase it to 0.7, and you see that the goodness of fit value goes down. You can say, okay, well, that looks like we're moving in the right direction. You increase it again to 0.9, and you see the goodness of fit goes even smaller, so the chi-squared number you get is even smaller. And you do that process basically until you reach the point that you find kind of like a saddle. So, let's say you continue to increase it to, 1.6 millimeters per year, and all of a sudden you see that the goodness of fit value that had been going down, down, down starts to go up. That tells you now that you're around the kind of around the velocity that provides the best fit to your age data. And again, this will be a little bit more clear when you start doing the process. But essentially, the repeating of steps 1 through 5 is just based on changing this advection velocity, with the idea that you want to try to find the point where you have the minimum value for your goodness of fit, which tells you that is the best advection velocity for fitting your age data.
Okay, it makes sense. I just don't know how would that be in on a code kind of thing. It's just what I'm trying to figure. I think wrap my head around how would you code that.
Yeah, well, I will. This is something that I still need to finish describing in exercise number 6, because it's as I mentioned, it's not quite ready yet. It'll be ready hopefully by this evening. But the idea with exercise 6 is that I'll lay out the set of instructions so that you basically build a code that does all of these steps. This is anytime you see something like repeat steps 1 through 5, it should hopefully pop up in your head that, oh, okay, if I have to repeat steps, this means these are a set of steps that I could potentially make a function for, or make some kind of script where anytime I want to do these 5 steps, I have my one thing I want to change, which might be my advection velocity, and then a bunch of steps that just occur. And if I make a function, for example, where I take only the advection velocity, I could then very easily change that and then have it go through these 5 steps. And so the whole point in exercise number 6 is going to be kind of building this numerical model, which is basically putting together all these pieces we need to do steps 1 through 5 easily. And then in exercise 7, I think what we'll be focusing more on is actually then applying this approach to try to fit our age data. So exercise 6 will be building the model, and exercise 7 will be more about applying the model. But there'll be some small testing of things in exercise 6, of course. Any other questions at the moment? All right, so if not, we can go back here. So back on the course page for lesson 6. So we've gone through the lecture slides on these first 2 things. Got an introduction to exercises 6 and 7, a little bit of background on low temperature thermal chronology. As I mentioned, if you go to exercise 6's page right now, you'll see it's not ready yet. Sorry about that. I'll have it up as soon as I can. But it's a new exercise, and I want to make sure that I try to find all of the holes in it before I post it, just so that you're not immediately confused. And that brings us here to the last topic that was going to be presented today, which is about this final paper. As mentioned, the tentative due date would be the 12th of January. I may bump that to the 14th just because that would be the end of the week. 12th is a Wednesday, I think. Yeah, basically the idea is to write a scientific paper style report on the results you produce in exercises 6 and 7. So for this, you can either use a Jupyter Notebook template, I'll show you that in just a moment, or you can use some kind of word processor like Microsoft Word or LibreOffice Writer, or whatever you prefer, to create the report. If you use Word or something like that, then there's some suggestions here to use 12-point font, single spacing, and the report length should be not longer than 6 to 8 pages, including text and figures. So what it should cover is presented down here below. So these are the kind of main sections. So there should be a short abstract, no more than 250 words. It kind of summarizes what you've done in the exercises and your main findings from your investigation of this data using the numerical model that you'll produce. Then there's an introduction, and the introduction is something like maybe 2 to 4 paragraphs. It doesn't have to be super long, but there you could kind of state, what you're trying to do. So in our case, we have this age data we're trying to interpret, and so you could say something about what the kind of overall goal of doing this is. So maybe something along the lines of trying to understand the rates of exhumation in the Himalaya in Bhutan over the last several million years. And you can, use things like out of the lecture notes to give some background information after you've stated what the kind of general problem is. And maybe then you would have a short paragraph that says what you're going to do. So that you're going to use some numerical model and estimate ages and compare them to see how well they fit the age data. Then there's a section about the geological background. I'll give you a few articles that you can look at for that. But essentially, for the geological background, the idea would be to say a little bit about the study area. So you can say things about the major faults that are there, and in the articles that are available to you, you can find some of that information. You can talk about essentially things like faults are going to drive uplift, rainfall is going to drive erosion. So you can say, what are some of these main drivers of uplift and erosion for the data that we're looking at. Then for the methods, you can basically talk about the computational part. So this kind of is a little bit about the code that you have. So, what equations are solved. So if you're going to do something like with the heat transfer equation, which we will, you might want to mention what equation is solved for calculating heat transfer, and any other relevant equations like the chi-squared misfit equation. The kind of description of what your code does is essentially what goes here in the method section. For then the results section, typically what you would do is have maybe something like a paragraph for each figure that you're going to present. So these are going to be the results of your experiments. So what we've done is calculated, for instance, different thermal chronometer ages, and so you might have some figures that would show how well your age data are fit by the predicted ages at different exhumation rates or advection velocities. Those things are basically synonymous for us. And so you can take figures out of exercises 6 and 7 and put them here in the results section and have maybe a paragraph that describes what's in that figure and a figure caption. The thing to note about the results section is it really is only the observations from the code output. It's not really about what they mean. It's just, we ran the code and here's what it produced. There shouldn't be any interpretations in the results section. The interpretation part goes here in the discussion. And so this can be a couple paragraphs or several paragraphs, depending how much you feel like writing here. But basically you just describe, again, what you've found from your results. And so you can have different kind of subsections or different paragraphs to talk about things like, how do the exhumation rates that fit the different thermochronometer data sets vary between the different thermochronometers. So the same exhumation rate might not fit apatite, uranium, thorium, helium, as well as the zircon, helium, ages. So there could be some variation in the rate that fits the different age systems. And you could also comment perhaps on how well the model predictions fit the measured ages in general. Any limitations, like we're using a one-dimensional heat transfer model, but of course heat transfer is three-dimensional, so you can talk about things like limitations in the design of the models, and other kind of drawbacks that would go there. Have you sufficiently tested your kind of hypothesis for how you think things work, or do you need more experiments, and so on. So this can be a couple paragraphs just describing, like now that you have your results, what do they tell us and what do they mean, and then finally you can conclude with either a short paragraph or maybe two short paragraphs in the conclusion stating the main things that you found. Then you can list some references. You should have at least 5 primary sources. So these are like 5 journal articles. Coincidentally, I provide a list of 5 or more journal articles that you can refer to, so you don't have to go too far from that list. And then at the end, if you want, you can include an appendix. I would suggest that you do so either in the form of a copy-paste version of your intro QG functions script file, or a link to that file. If you're using the Jupyter Notebook template for the exercise, you can just have a link to the intro QG script file, intro QG functions script file. And yeah, that's the kind of overview of what goes in the final paper. As mentioned, there are scientific articles. You can find these on the course page. If you click there, you'll find, I think there's 6 articles here. You happen to need 5 that you'll refer to in at least 5 in the final report. So, if you don't want to use anything other than what's here, that's possible. And maybe I'll also note that there is this template for the paper that can be used. It's just like another assignment in the course. And what you'll see if you go to this link is, well, if you click the GitHub Classroom link, you'll make your own copy of the final paper. And you can then go here and you'll see what the template looks like. It has basically all the information that was just present on the web page. There's a spot for your title, your name, the date, and then there's a cell here with some paper instructions that just kind of lays things out, and you can delete the cell before you submit the paper, but it kind of tells you what to do in similar way to what was on the web page. And then here's the different sections. And I would recommend you keep the section headings, but you can of course delete all of this text under here that describes what should go in that section. That can be deleted. The advantage in my view of doing things in the Jupyter Notebook is that you can actually produce your plots by calling the functions that you produced in exercise 6 and 7. So it's a very transparent way to do things like generate the plots and show the results of what you've done in those 2 exercises. So you could include the figures from the exercise if you want as image files, but you could also import your intro QG functions script file and then just run in a Python code cell here in the results some code to produce a plot that you could then include inside the report, so that the notebook really contains everything. It has your code and everything to produce your plots, which is a really nice way to use these kind of Jupyter notebooks. So I would encourage you to use this, but of course you're free to write it in Word if you prefer. And if you write it in Word, I suppose I'll have to come up with a place for you to send me a copy of the final report. I guess it could come over email, but I'll see if I come up with a better solution by next week. The one other thing I wanted to note about the final paper is down at the very bottom, there's a link here for the grading rubric. This is the sort of grading table that's used, so you can click on that link and you can see what each section of the paper will be scored on. And that might be useful just in terms of when you're writing to figure out how much each section is worth and where to put your efforts to make sure you get as many points as you would like on the final paper. At this point, I think I'll again ask, are there any questions? We can, of course, talk more about the final paper next week as well, but yeah, do you have any questions at this stage? Seems like maybe not. So, okay. If that's the case, then I'm hoping that means you're not just totally overwhelmed and freaking out, but rather just don't have any questions, because a lot of the information is here available on the course page. What I will say is, yeah, I'll get to work trying to finish up exercise number 6, but probably it's going to be available sometime this evening, most likely, because it does need some extensive testing before it can be turned loose for you to start working on it. But then hopefully that won't be delaying you too much from getting started. If it's not available till, for instance, this evening, I'll probably just accordingly bump the due date for the exercise back a little bit, like was the case, I think, for exercise number 3, maybe, or I think it was exercise 3 that might have been similarly delayed. So sorry about not having exercise 6 ready to roll, but I trust me when I say that it's much better that I try to catch as many of the bugs as possible before I let you start working on it, because afterwards it becomes quite challenging if there's sort of things I've overlooked that are significant. So yeah, if there aren't any questions, I think maybe that's it for today. And we will continue next week at our normal time on Monday at 2:15 with the lesson number 7. And I think then, yeah, I can't think of anything else. So if you have questions about exercise 6, again, you're always welcome to come on Friday to the exercise sessions. Those will continue to happen as they have been. And as soon as exercise 6 is up, I'll post a message in Slack and let you all know. And we'll catch you here next week if I don't see you on Friday in the exercise session. So yeah, see you next week.